Well, it's time, folks. Welcome back, everyone. I hope midterms week is going great for folks and we're getting caught up in that kind of stuff, not losing too much sleep. Any questions or comments at all, folks, to start us out? Okay, well, we're nearly done with chapter 15, but I think it's worthy to spend a little bit more time on there, expand on a couple of things, because we also have our upcoming exam. It's going to involve chapters 14 and 15. And I wrote here a little note to say, if you do indeed complete assignment 6 early, say on March 5th or sometime early on March 6th, I'll attempt to grade it as soon as possible and send you back the feedback. That way, that will help you out a tremendous amount on studying for exam 2. And if I was in this course studying for exam 2, that's pretty much where I would start. I'd want to make sure I have assignment 6 down pat. On your assignment 5, that's going to be graded shortly and returned, I'd want to make sure that I understand anything I missed there and all my work there makes sense. Then and only then would I probably start looking at, say, this kind of stuff, the sample exam 2 problems. Pretty much all these are the lecture notes where I rewrote them so that they would look like an actual exam question. I took out all the notes, took out all the formulas, and anything that used RStudio, the information's already published right on there. I'll post a second set of sample exam 2 problems for folks that would like more variation. That'd be helpful too. And, well, I think I ran out of comments on that other than another thing to double check is the exam 2 formula sheet. For this exam, this will be the last page, so it's not something you have to print out to bring to your exam. But while you're studying for the exam, it might not be a bad idea to have it available, maybe even print it out, since you want to know just how to navigate through this document as you're taking the exam. It'll have information about confidence intervals, hypothesis testing, and type 1, type 2 errors. Regan asks, in working on transferring my document into a PDF to send to you, it's just taking it. Oh, gotcha. Thanks. Other questions so far? Okay, so that's going to be our sheet that's provided. And this is a good document to have. And as you go through studying either these problems right here or going over your homework assignment problems, pay particular attention to what's not there, the things that you would have to memorize for the purposes of the exam. Well, other questions or comments so far, folks? You bet, Regan. Okay, other difficulty about this class is it's a non-standard class for sure. I mean, really, this is 2 classes running as one single time slot, so it's kind of odd in a certain sense. For folks registered in this section, I'll be giving an exam in person. They'll be in this classroom next Wednesday. For folks who are doing the online section, we won't have a class, and what will happen is on Monday, I'll send the exam over to the Pocatello Testing Center, along with the roster and that kind of things they require. Then I'll email you to contact the testing center like before to schedule time to take your second exam. In other words, it's going to be exactly like before, but it's good to have some reminders on that kind of stuff. Any questions about taking the exam, knowing where to be, that kind of thing? Okay, well, the good news is it gets easier each time we go through this. And like you noticed before, I'm not really trying to make a huge exam out of this stuff. Pretty much it's going to be the major things that you need to know if you're completing a homework assignment. These are the things that you shouldn't really have to look up. So it'll be kind of the more standard kind of questions that you could expect on the second exam, kind of like on the first one. And really, when you look at the design of this class, really it's more about the homework than even the exams in a certain sense. The exams are not weighted quite a lot. The final exam is pretty minimal for this class. So really, if you're nailing the homework, that's really where you're getting your most contribution to a higher grade in there. That's kind of weird to say. And doing well in the homework is going to affect your exam scores tremendously because the problems are based heavily on those homework questions as well. I think at that point, I kind of ran out of things to say about the second exam. We'll jump back into chapter 15 to finish this one off. Then we'll see if we can make some headway into chapter 17, but I'm not going to try to drive really very hard into that chapter, mainly because when we return on Monday's class, this will be our next impromptu kind of review day, an informal review day. It's up to the students in the class which questions we would like to take on. And if we run out of questions, we'll just continue to go through chapter 17. So that's our plan so far. Any questions or comments at all, folks? Okay, well, let's take a look at where we left off in chapter 15. The major thing we got to was we found a way to find the power of a test to come out to approximately 95% by taking a sample size at 31. So we want to expand on this a little bit, answer some concept questions down below. But if you're like me and you see this kind of diagram, that's quite a lot to look at all at once, right? So I think just to get started after coming through the weekend, we should investigate this diagram and remind ourselves what's going on. And here's the second thing that's kind of rough about looking at a diagram like that. As the diagram sits, well, you can stare at it and stare at it and stare at it for hours, but it's incredibly hard to learn just what's going on from a static image like this. Really, the best way you want to learn this kind of stuff is by just drawing it all over again. Let's start from scratch, show how it all works, because it's more about the process, how the diagram comes together, than it is looking at that one static image. So back to square one, here's how we're going to go through this. It says, suppose that differences smaller than a pH of 0.3 are not considered to have practical significance. Well, the null hypothesis was at 5, and if we're concerned about things larger than 0.3 being now having practical significance, we're concerned about this specific alternative of 4.7. Why not 5.3? Why did it go below? It's because our hypothesis test was a left tail test. We're looking in the direction below 5, and for a practical difference, or let me say that better, significant difference of 0.3, we just subtracted that to get this value here. Next thing that happens is there's now two distributions. The one on the left gives us this kind of diagram. The central limit theorem tells us what the values are going to be, so we can actually calculate them using the syntax below. Down here will be the value of 5. And already we need an extra special symbol. Forget that. We need to look at the hypotheses as we go through this, so sorry for the constant scrolling. That's always a little bit jarring, I think. Okay, less scrolling now that we've got this. I'll just park it down below. So we had a 5% level of significance, and because, again, this is a left tail test, what we do next is take this region and this is going to be alpha at 0.05. Now, if this was a right tail test, we would have had to put the value over here, and if it's a two tail test, we'd have to split it into either side. Getting the two tail test power computation through is not terrible, but it's a whole lot of extra syntax. For us, the takeaway about this is more just how it will go with a left tail test and a right tail test, so that we have a picture in our mind when someone says the power of a hypothesis test. So I won't ask a question with a two tail test, not on the homework nor the exams. It'll either be a left tail test or a right tail test. So this is what it looks like so far. We'll call this location here Z. Now this is where it gets interesting. The diagram starts to get involved, because we drew this distribution if the null hypothesis right here is true. We need to write a related distribution if this specific alternative hypothesis is actually true. So let's draw this in. They'll look about exactly the same shape, but I'm going to move it a little bit closer than I had on the other diagram. I feel like it's a little bit easier to show what's happening inside here if we draw a shape that looks like that. Significant amount of overlap. Means there's not a lot of power here, but we can tell the difference between the different regions. So now that we have this curve right here, let's see, this is a value at 4.7 coming from the mean in this location. We can now describe what this area represents. So if we calculate a test statistic and it ends up in this location, we're going to reject the null hypothesis. But if we calculate a test statistic and it ends up in this location, we will fail to reject the null hypothesis. If this is actually true, that alternative, and this will specify the probability of that actually happening. And this would be beta, probability of a type 2 error. Lives right in this location. So now with beta down, the last thing you have to do is take another look at this vertical line segment. It went up and hit the curve for the null hypothesis, but it continues to go up until it hits the curve right here from the specific alternative hypothesis. Let's carry that border a little bit further in. And finally, this right here is what we refer to as power. It's difficult to shade because it is below the alternative hypothesis. So it's going to invade this location right here from the null hypothesis distribution. And this is what we mean by power. We did it, folks. It's good to redo these diagrams. That's really good practice. So if you can create that diagram from scratch, I would say you have a really good head about what power is really trying to say. Any questions at all with the diagram so far? Okay, then what we did next was we actually calculate all this stuff. Let me get rid of these temporary hypotheses. Z is just going to be a Q-norm computation. It's really pretty quick. But once you have Z, you just need the area to the left of it, this purple area. That's what the power is, so we use P-norm right at Z, the cutoff point. But watch out for these values right here. It's going to describe which parameter values you actually throw in, and they come from these distributions up above. So we did this, we calculated at 91 power. Let me see if I can fix this document. There we go. Using that syntax, here's what the power came out as. We said at least 95% because the question was more about at what sample size is required. So the answer to the question was sample size 31. But the actual power we got went like this. It came out as 95.50% altogether at a sample size of 31. So again, that's our review on the question. Kind of a good one to get us caught up on before we look at the concept questions related to that diagram. But any questions at the moment? Okay, now let me take this diagram and see if I can somehow walk it down. Sometimes this works, sometimes it doesn't. Microsoft Word is weird with digital ink occasionally. For these concept questions down below, there's multiple ways you can answer them and think about them, and each way is pretty valid. We're first going to think about it geometrically, then we'll see if it fits our prediction by verifying it using the syntax above right here. Again, either way you decide to think about it is, I'd say, a fine way to go about the problem. So now let's leave this up to the class to see if we can suss out what's going to happen here. It says if alpha decreases, that's the significance level for the test. That means our type 1 error probability goes down. But what will happen to the power of the test? Will the power go upward or will power go down? That's a tough question, but here's how we can think about it. Alpha decreases. That means this area is getting smaller. If that area is getting smaller, that vertical line segment would have to move to the left like that. But that means the purple area is going to get shortened because it stops right at this barrier. I mean, that's a true barrier. It has to go, that's the wrong one. It has to go all the way up to hit this curve right here. So shrinking alpha is actually shrinking power. Does that make sense to folks at the moment? Okay, visually it's something we can look at, but this is such a busy diagram that it may not be completely straightforward by looking at this. So let's take a look at it from the other point of view. Now back to RStudio. Our power's at 95%. I did make one change on the syntax I should alert everyone about. I had a 0.05 here, but I think it makes sense to put in actually that value of alpha. Makes everything run a little bit cleaner. So I put alpha into that location right there, right where the Q-norm function is. So we just ran the syntax at alpha at 5% level of significance. We have a power of 95%. So let's drop that. Alpha decreases, so over here, let's decrease it to a 0.01. Run the syntax again. And sure enough, power went down. It went down by a lot. It looks like more than 10% on this thing. Well, we also dropped alpha by a significant amount as well. We have to keep in mind. So the short of this one we can say is power will decrease. And we can give a pretty in-depth explanation. We can describe what happens geometrically as alpha shrinks and that kind of thing. But if you see this as an exam question, it won't say explain your answer. You can just say power will increase or not increase. No explanation is necessary. It takes a while to really put our thoughts into words for that kind of thing. Let's try this out again. This one's a little bit trickier. It's saying if the effect size decreases. Let's pause right here and show what would happen with that. We had a null hypothesis that mu equals 5. The effect size that they gave us was 0.3 pH value. What that returned to us was a specific alternative. We still call it HA, but we'll set mu equal to, we went to the 5 right here and just subtracted 0.3. So it was 4.7. So now they're saying right here, if the effect size decreases, means we're shrinking this right here, what should happen to the power of the test? Should it go up or should it go down? Let's leave this one to the class. Any volunteers? What should happen for power if we make that smaller? Hannah says increase to the power. Any other volunteers? Okay, thanks for mentioning that, Hannah. I think this one is actually, you know what? I'm not completely sure. This is one of those tricky ones where you have to really look at it carefully. Or there's a third way to kind of think about this. If you say a small effect size, that means you're trying to look at differences that are really pretty small now. You might have less power if you're looking for small differences, but if you had an effect size that was huge here, like a pH of 2, you might not need too much, a very large sample size to actually detect that. In other words, power should be higher. But then again, that just seems like we're just kind of waving our hand at the problem. We need to actually see this in action if we're going to believe all that as an argument. So let's show what happens if the effect size does in fact decrease. Let's say below, suppose the effect size is, let's just say 0.1 for a pH. That would change our specific alternative. We would be taking the value of 5 here, subtract the 0.1, and our alternative hypothesis is now mu equals 4.9. Now, what does that do for us? It goes to this diagram at 4.7. We're moving it to a 4.9. So this whole curve moves like that. I'm not conveying exactly what's happening because also the purple area is moving to the right, but it still stops right at this boundary right here. It can't proceed any farther. You're pretty much fixed whatever alpha was set as. And so now power has diminished quite a lot of this diagram. It's always going to be the area right here. So we'll put down if the effect size decreases, power will decrease. Deserves another exclamation mark. I think these are pretty tricky questions. Does that make sense to folks, seeing it on the diagram side? Okay. Oh, I was going to Control Z that, but I think that would also undo the text at this point. I'll just leave it like this for the moment. But if you're not sure, if the diagram just still looks a little too crazy to suss out what happened to power, good news is we could just put down a specific alternative like before and just see what happens to power down in the syntax. In your homework assignment, again, this is a perfectly valid way to answer and think about these kinds of questions. So over here, let's go and fix alpha. It's still at 0.05. We'll run it again, so that's our benchmark. We have 95% power. But right here at 4.9, we need to figure out where that's going to change our syntax. And the change is going to be right here, where we have a specific alternative. I usually designate that by writing U sub A to say alternative hypothesis. So we're going to put a 4.9 in the position of that 4.7. There it is. Let's see what happens to power. Our power this time is diminished quite a lot of this time. We can kind of see it on this not really great sketch diagram as well. And that's kind of the rationale behind this. If you have a very small effect size, your power is going to diminish unless your sample size goes really high to resolve that really small difference. But at a high effect size, you don't need very much samples at all to detect that. We could demonstrate this right here. Let's suppose this was a 4.0. That means the effect size was 1 in pH. That's quite a large leap. That's a logarithmic scale after all. And now power, it's not 1, but RStudio had to round now because this is a 0.999 with so many nines that the precision of the machine has failed. They're just going to round this one to 1 at this point. Okay, so that's power when the effect size changes. And because effect size is pretty hard to think about, let's use some yellow color coding. It's affecting this portion right here. Well, any questions or comments, folks, with the changes on this one? Okay, well, let's try this once again. I'll just have to delete that and get another version to copy. Okay, looks like this is kind of the last honest concept question. I can get that to fit in there. Let's just move it to the next page. That might be better. Okay, so like before, this is a good one for the class. It says, if the sample size decreases, will the power of the test increase or decrease? Any volunteers for what should happen in that situation? I agree with Jackson. This will definitely drop power. And this is one that's not too bad to think about. Intuitively, we can say, well, small samples are giving us less power intuitively in the hypothesis test, so that must be the case. Let's say this right away. Power will decrease. So that's one kind of explanation, but you'll notice that's a hand wave explanation. I'm not saying exactly why power decreases. I'm just saying it should decrease if you have a smaller sample size. So what really happens? Well, it's all about the central limit theorem. Recall that that curve by the red dot, I mean, both curves really, are distributed this way. It's a distribution, a sampling distribution for the mean x bar. They're distributed normally with a true mean of 5 for this one. This one had a different true mean on the left by the red dot. Then we took a standard deviation, which was 5, and here's where the change occurs. There's a division by the square root of n. So what happens if this sample size decreases? We'll get a smaller number here, but if your number there is smaller, that whole thing gets bigger altogether. If this gets bigger altogether, that affects the width of this distribution. Let me see if I can stretch this out to show. This one will stretch out in a certain way, and so will this one by the same exact factor. Oh, I grabbed the wrong thing. Let's see if I can grab that. There we go. Kind of hard to convey it exactly, but that's about what's going to happen. Now for the value of z, z is also going to have to move because the area is just going to be 5%, no matter what. So it's got to move. Oh, it's really hard to get these just right. It's got to move into a location where it now becomes 5%. But if it moves there, that blue boundary is now affecting power majorly. It's going to wipe out all of this stuff, and power only goes this far anymore. So the smaller the sample size, the wider your distributions are, and now power starts to shrink and suffer more and more the smaller the sample size gets. So in a certain sense, that's what's going on if you drop the power. That's why we like a large sample size. On the other end, if the sample size became huge, you have to worry about the square root factor. You have to grow this by a lot to cut down the whole thing by a certain amount. But as n gets larger, this whole quantity gets smaller, and you get a picture that looks like this instead. This is the effect now. Still has to have an area 1, so it's going to do something more like this. But that's what will be what will happen if your sample size gets really large. We'll start to see these kinds of things. That's kind of poorly drawn, but you get the idea now. Power is going to be almost entirely contained inside here, and now you're going to have really large power once your sample sizes are large. Let's bring this back to normal. It's really kind of hard to see these things on the diagrams, but it's also fun to just throw it into RStudio and see what happens. So just for the sake of finishing this off, let's do just that. Bring that back to 4.7. We run this again. Okay, that's the power we're expecting. And this talks about decreasing the sample size. So let's decrease it to 3, something kind of extreme. And yeah, power, it hasn't dropped by a lot. Well, you consider that the sample size is just 3 now, but that's definitely a decrease in power, a substantial one. Well, we did, folks. Those are the weird concept questions we need to think about that go along with the power of the test. There are some questions like these in the homework, and they can certainly also be exam questions for exam 2. But having seen all of them, here's a great way to think about all of this. You might have noticed something, that there is a common direction with everything. If something decreases, say if the significance level alpha decreases, so does the power. If the effect size decreases, so will the power. And if the sample size decreases, so will the power. So those 3 quantities change in the same direction. So if I change the question by saying alpha increases, so does power. And if the effect size increases, so does power, and so on. Don't know where that beta came from, but we should get rid of it. Well, any questions, folks, with those concept questions so far? Okay, well, last part of the notes, and congratulations, we're just about done with chapter 15. It's asking, suppose the hypotheses that are to be tested look like this. The major feature is, this is now a right-tail test. We want to know, what should your syntax look like? Pretty much the whole purpose to part G is, your homework question is a right-tail test. And this is a very, very common question. How should we fix our syntax? So I figure we might as well make a real question out of it and fix it right here. So if everything is kept the same, the significance level alpha, the sample size, the effect size, but we're dealing with a right-tail test, all we have to do is go inside right here, put in lower.tail equals false, and go over here, do the same adjustment. Lower.tail equals false. Reason being, if it's a right-tail test, everything up here kind of switches around. This blue area moves to the right tail. This whole curve would move to the right-hand side. So the diagram's been flipped around, which means add this last bit to the syntax and you'll have the right computation. Well, we did it, folks. Congratulations, everyone. I think chapters 13, chapter 15, they're some of the harder chapters in this whole course. Beyond here, it's not as bad. It'll be a little bit more similar to what we were doing at the start of the class, except we're now getting into new territory. Any questions at all before we close out these notes? Okay, let me save these up. And now we'll take a look at what we're getting into in chapter 17 finally. And we've been hinting quite a lot that chapter 14, really its whole purpose is it's definitely introducing and just introducing confidence intervals and hypothesis testing, but there are problems in that procedure. There were problems that were not noticed for quite a while, in fact, and that was okay for a while because the central limit theorem is effective. If your sample size is around 30, it's highly effective. But people notice problems. Here are my 2 favorite heroes from the world of statistics. Ronald Fisher was considered a big genius to a lot of people, and he's thought of as the founder of modern statistical methods as we know it and use today. But there was something that even he missed. William Seeley Gossett was an interesting individual because he worked with small sample sizes. He worked for the Guinness Brewing Company, and you can't do a sample size of 30. That costs too much in those kinds of experiments. So for sample sizes around 3 and around 4, the methods that we described in chapter 14 do in fact break down noticeably. He realized that that was happening, and he found out what the correction really was. He called it Stewing's tables. And the reason he did that was the Guinness Brewing Company considered his knowledge on the T distribution really a trade secret at that point. But him and Fisher were not emailing, they were writing actual letters to each other, and they believed that this knowledge had to be set free. Fisher believed that this was a real logical revolution, the T distribution. So they did just that. They defied the corporation, the Guinness Brewing Company, and published the results regardless. In my view, that's pretty amazing. And that's why I consider him a pretty decent role model for the sciences. Some knowledge just deserves to be set free. That's what we're getting into in chapter 17. So let's take a look. I have a lot of different things in chapter 17. This thumb drive right here is duplicated over here. These are the standard lecture notes. These are the data sets that we'll be using. And these are just optional reading things that you can come back to if it's helpful. This takes all the syntax you'd use for the t-distribution, puts it in one place. And this is a one-stop shop for anything you want to know about confidence intervals, hypothesis testing using RStudio. This one is just comparing the normal distribution against the one we're about to take a look at. So we'll come to that document soon. But first, here's what happens when we start off these notes. The very first thing we should talk about is what was the problem with our methods in chapter 14. So let's take a really close look. It said, gather a simple random sample of size n from a population with a mean mu, standard deviation sigma. From the central limit theorem, the sampling distribution of the mean x bar is distributed in this way. Now we know that that approximation improves with the sample size increasing. In hypothesis testing, we use that as a test statistic. And these are all measurable values, they'd be provided. But here is our major problem. That value right there, sigma, has to be provided in some way, somehow. So it's not exactly true that both parameters mu and sigma are always unknown. There's certain contexts where you might know the value of sigma. IQ tests are standardized for sigma to be 15 for a population. Mu is always considered unknown. If you knew the value of mu, you would not do statistical inference at all. Your job is done. You found out its value. But that being unknown is a huge problem for us because of that right there. If we are honest with ourselves that sigma is an unknown parameter, we cannot calculate the test statistic z. People found a workaround, and this is what they did. We're going to estimate the test statistic z, and they did get in trouble for a while. Here's how we're going to make that estimate. Let me actually highlight differently. There we go. We need to say sigma is approximately equal to something. Any volunteers for what should go right here? Here's a small hint along those lines. For the other third parameter mu, this one's approximately equal to the statistic x bar. We need to do the same thing right here. Anyone see which statistic should go into that location? Exactly, Aspen. We're going to put in the sample standard deviation S right exactly there. And historically, this is exactly what was done. People just used the sample to estimate sigma, and they thought nothing of it. That's just fine, right? No, it's not. We mentioned that we made a big deal out of this. That estimate is useless unless you can describe the error in making that estimation. Same exact problem right here. If we don't say how reliable that is as an estimate, we should be worried if our test statistic z is even giving us the right numerical quantity that we're expecting. We could be just fooling ourselves. But again, if your sample sizes are higher, when they did this historically and just put an S right inside there, they got away with it. They couldn't really detect that there was a major problem. With small sample sizes, even around 10, it's noticeable that there's a big problem with doing this. There is an extra estimate right here, and our confidence intervals should be wider to reflect that. So because of this, the statistic we're using is no longer z. It's called a t test statistic. So t is the t test statistic, which estimates that old statistic z. The way we calculate it is t equals x bar minus mu naught divided by s. So there's our estimate right there for the value of sigma over the square root of n. And black doesn't make sense there. Let me go back to blue. So that so far looks like the correction to our problems, but it isn't quite there yet. The trouble with putting S into this location is we're not going to call it Z any longer. Z means we're dealing with the normal distribution. So Z is distributed as N01 as a random variable, but T does not follow the normal distribution. It was a whole new distribution that it follows, and that was the heart of William Seeley Gossett's actual work for the student T distribution. So this is not distributed normally. So we have a couple extra tasks though in this chapter. We have to find the real distribution that T falls under. Then we'll reformulate our confidence intervals and hypothesis tests using that correct distribution. But any questions at the moment? Okay, before we look at that distribution, this quantity right here suddenly becomes really important. We're going to call it a standard error, and we'll be mentioning standard errors in chapter 17, 18, 19, 20, and so on, but they are all different kinds of formulas. What the standard error is always trying to do is estimate this right here, sigma over root n. But if we're looking at different kinds of data or different kinds of data, it may not be a sigma over root n there. It might be a different quantity through a different central limit theorem. But regardless of all that, in chapter 17, if we are dealing with quantitative data with one single variable, this is what the standard error is going to be. We write it out as SC to stand for standard error. And there's no multiplication here. Think of this like function notation from college algebra calculus. This is saying standard error of X bar to signify which standard error formula we're using. There will be several of them. But for our section, it's chapter 17 rather, it'll just be this right here. We put in S in that location, divide by the square root of n. And so now we're dealing with the standard error. Let me see if I can move this slightly better. There we go. So all the standard error is trying to do is, once again, make this approximation happen. So now that we have the standard error, now we're going to see how this all falls together. If it's not normally distributed, we'll have to take a look at the new distribution, the so-called T distribution. Any questions or comments at the moment? Okay, we're nearly done putting together all the threads. And here is the T distribution. So it says to start out, suppose you have a simple random sample, n individuals from some population that has a normal distribution. We will take that off. And once we take off that assumption, we'll start considering the robustness conditions for our confidence interval. So at the moment, it's saying distributed normally with a mean mu, standard deviation sigma. We have our one sample t-test statistic calculated right here. And here's how we say where the distribution comes from. This t follows the t distribution with n-1 degrees of freedom. That's a mouthful. So just like how we can abbreviate the normal distribution with mean mu, standard deviation sigma, into just n mu sigma, that whole statement can be written out this way. This is saying a variable t is distributed with the t distribution with n-1 degrees of freedom. So pretty decent shorthand. But here's the bad news. Just like with the normal distribution, it was a pretty complicated curve involving an exponential function and another composition. This one is massively worse. If you actually want to calculate a t distribution by hand, here's the formula. Some folks might recognize this from differential equations, from probability theory. That's the gamma function. That's just one portion of the formula. The gamma function itself is an improper integral defined in this way, involving the sample sizes n and such. In other words, it's fine to write it down. This is just for curiosity's sake. But I would absolutely consider all of this. Let me try slightly better. Yeah, from right here, I would consider all of this optional reading. This is for the curious. How is the t distribution defined? Well, it's defined in this horrendous way. And if you want to find the area under the curve, you have to calculate this many times to approximate the curve to get its right area. The good news is this has all been numerically implemented in a very, very fast process through RStudio. So we don't have to worry so much about computation. But then the bad news is if we're throwing everything into RStudio every single time, you're going to lose the mental image of what's really happening in the background once you're actually using the t-distribution. And for that reason, we have this file. NU sigma versus t n-1. Well, that's the actual PowerPoint. I don't think I want to open a PowerPoint. That just seems kind of rude. Let's use this one. This is a PDF converted out of a PowerPoint. It's meant to be kind of a slideshow. We won't do a lot of these, but seem to work out for a comparison's sake. Our goal is to see what happens with the standard normal distribution as you compare it against the t n-1 distribution. So on the next slide, here's what it would all look like if you had a sample size of 2. That's kind of unrealistic in a certain sense. Instead, you're usually looking at, say, sample sizes a little bit higher. But suppose you were in this situation. Yellow is the curve for the standard normal distribution. So this is the curve we're used to working with. And the blue curve is the t n-1 distribution. So that's the t distribution with 1 degree of freedom would be that blue curve right there. So now we mentioned when you do this kind of work and take a parameter like sigma and just simply approximate it with s, we need to reflect that that is an approximation on top of other approximations in our process for calculating a confidence interval. The way we have to really make this work out right is if there's an extra estimate right there, our confidence interval must be wider to account for that uncertainty right in that location. And here's how it's done. Let's suppose confidence was at 0.95, since it's decently okay to draw that one. I want to focus on the yellow curve for this to start out, so N01. So at 95%, I would say, yeah, right around here, -2, +2. We'll go up to the yellow curve here and here. And this is where you would get your z-star. About 1.96 for confidence equal to 95%. So that's what the picture would look like. Now, if we are honest that we made this mistake, or not mistake, but that estimate, we're not on the right curve any longer. This was William Gossett's work. We're on the t n-1 distribution in fact. So here's what change will come. Let's use this color that'll pop out a little bit better. If you're on the t n-1 distribution and you're still trying to trap central area of 95%, then you're on this blue curve and you have to move out substantially farther to the left. Say around here, I don't know the exact location, this is just visually estimated. And you'd have to move symmetrically the same distance to the right, so somewhere right over here. And this would be the value for t star at the same amount of confidence. Let's reconfigure this and shade with the new boundaries. So this is what happens whenever you make that estimate, which we'll do over and over again in chapter 17 and beyond. We are punished, and we should be, because the extra uncertainty in the problem should make t star wider. Z star and t star go into these locations. The confidence interval is of the form x bar plus or minus the critical number multiplied by a standard deviation or standard error. If we're using the actual standard deviation, that means we're in chapter 14. We used sigma, in fact. We used standard error. That's chapter 17. We did not use sigma. We estimated with S. So the critical number we actually put inside is t star right here. That's absolutely going to make the width of the confidence interval wider, as it should, because then that accounts for the uncertainty. So that's the idea with the t distribution. It's hard to calculate out of it. And when sample sizes are low, it's absolutely required we're using the right distribution. And really, even if sample sizes are higher, we should still try to be as accurate as possible and still use the t-distribution when appropriate. But let's take this slide right here and just drop it into our notes. This will be our discussion right here. Not so much about the formula, but more about the mental picture you want to have every time you use the t-distribution, something like this. Well, any questions at all, folks, with those diagrams? Okay, going back to that PDF, let's see what happens when the sample size does in fact increase. Recall from the central limit theorem, we're expecting good things to happen at around sample size 30, and this is what begins to happen. So let's bump it to sample size 3. Kind of hard to see what the change was, but right here, the blue curve, which is the Tn-1 distribution, moved up closer to the normal distribution curve right here. This curve in yellow will never change. It's unaffected by sample sizes, but the t-distribution is. So go for sample size 3 to sample size 6. And notice it's starting to, well, kind of match up. Still, T star would be significantly larger than Z star on this picture. But at higher and higher sample sizes, it starts to become difficult to tell apart the distributions, at least on this terrible image. This is not very high resolution, and neither is this monitor. Go beyond 30, I don't think I have a slide, but if we did, the Tn-1 distribution is going to look a lot like the N01 distribution. You'd have to actually calculate probabilities in RStudio to see the difference between the two. There still is, and that's why we're now going to use the t-distribution exclusively for doing a confidence interval or hypothesis test with one single mean. But it was kind of cool to know that this is kind of where the central limit theorem was doing for us. It was helping out, but it also hurt sciences because for a while we couldn't detect there was a problem around this range, the low sample sizes. A lot of people were in this range instead. Well, we did it, folks. That's our brand new distribution. We have a couple of new things to think about, standard error that go along with it. But finally, we can now take a look at the full procedure. Once I find where the page break is, there it is. Let's take a look at the robustness conditions in just a moment. I think everyone is more excited to look at what happens to the new procedure. It looks a lot like the old one. So if we draw a simple random sample of size n is going to go inside here for standard error into that location. The confidence level C is going to dictate the value for T star. And really, that's the only change right here. It's the same kind of, well, let me say that again. There's a couple changes, right? The fact that we have a standard error means we're not using sigma. We're not even looking for a value of sigma. And a good problem going forward probably won't even mention sigma. So there's really two different changes we have to track. It's this one. We have a formula for the standard error. Sorry, try to come up with the right color. Let's use green. And we also have the value T star right here. So those are our two new changes. Any questions at the moment about those? Okay, so if that's really the only major change, and standard error is just a slightly different formula, then getting good at this new confidence interval procedure just completely boils down to, can you calculate T star under different scenarios? So that'll be the first thing we'll practice. Then we'll look at a whole honest confidence interval problem. So we'll come back to those robustness conditions, but for the moment, let's focus on dealing with T star right here. It says, what critical value T star would you use for a confidence interval for the mean and mu of the population in each of the following situations? Suppose we have a 90% confidence interval on this one to start, which is a sample size of 10. What I would probably do right away is just do a really fast sketch. You wouldn't have to do this every time. This is more for the notes to show why the syntax ought to look the way it does. Kind of a reminder of how it went in chapter 14. So the curve I'm trying to draw is the t distribution. To convey that, I try to make it slightly more heavy-tailed, but that's not as important as making sure you have 0 here that matches with the standard normal distribution. Next thing I'd probably want to do immediately is, if they give us a sample size of 10, we should say that the degrees of freedom is That's the nicest formula you could ever ask for. It's a little bit worse in chapter 18, but this will just be a 9. So this is the T9 distribution. So that helps us out getting started. Next thing we want to do is work with the confidence level. If it's at 90%, then we'll just capture central probability at 0.9. So here's the sketch for that. Probably should go a little bit further to the left, a little bit further to the right, but we're not trying to do perfect proportions for areas, just trying to convey the information. So let's stick with this, 0.90 for central probability. Finally, our ultimate objective is to get this, T star. If we can get it, our job is done. So now, here's the next trick. You can say what the area is on the left tail and the right tail pretty rapidly. You just take the confidence, subtract it from 1, divide it by 2. So go to this location, and there's the same amount in this location. Clearly it's a 0.05, but we want to write the syntax that will work for any confidence level. So I'm going to just leave it like this, 1 minus c divided by 2. And then finally, back over here to get T star, which you'd probably put in is, I'm going to put it in negative to start, so I don't have to use lower dot tails false. I'm just going to flip the sign negative. If this was the normal distribution, we would have written Q norm. We're still going to use Q because we're looking for a value on the horizontal axis. We're looking for a particular quantile, in other words. And if it's not the normal distribution, but a T distribution, you just throw a T there. That's kind of nice in a way. So that's kind of how RStudio likes to operate. The letter in front is going to say what kind of probability, P for P norm or P for PT. If you're doing critical numbers, it'll be either Q for Q norm or Q for QT if you're dealing with the T distribution. So give it that value. We'll go over here and throw in 1 minus c divided by 2. If this was the normal distribution, that's all the syntax you will need. But for the T distribution, you need one extra thing. The actual value for T star absolutely depends on the sample size because the shape of this depends on the sample size. So you need to put the degrees of freedom in this location. So that's pretty much what the syntax looks. And from there, it's really pretty fast to calculate all of these. Any questions at the moment, folks, with the organization here? Okay, before we go to calculate this one, let's see what we did in the past. At 90% confidence, let's go to chapter 14. Here we were connecting the central limit theorem to our methods. And we found at 90% confidence, the critical number was 1.6449. Some people might have memorized that, but that's kind of amazing. A lot of people end up memorizing this one, it turns out, 1.96. So coming back over here, we're expecting something quite a bit larger than 1.6, because with these methods, we're using a standard error. There's extra estimations going on. So let's see what it comes out as. For the syntax, let me scroll just a touch. I'd usually start off kind of like this. Throw in the sample size. This one's at 10. Then you can throw in the confidence. This one's at 0.9. If you decide to reuse the syntax, those would be the first two values you'd always want to change. Then everything down below is just going to calculate normally. Let's just put a border here to kind of change those values above first. Then last thing, we'll throw in that syntax, negative QT, 1 minus confidence divided by 2, and degrees of freedom. I'm noticing one problem. I didn't actually store degrees of freedom here. Let's put it in. Degrees of freedom gets n minus 1. So now this syntax, all you have to do is adjust the two top values. It'll give you all the critical numbers you could ever want. That's kind of the nice thing about RStudio. Some people might be familiar with how we did this in the past. We would actually look up a table of T values and find the right sample size with the right confidence to get a shoddy approximation. It's not a very good experience, but for us, this is all we have to do. Hit Control A, Control Enter, And that's your critical number, 1.8331. The one from chapter 14 was about 1.6 and some change. So it might not look like much, like we're not increasing it by very much. But keep in mind, T star multiplies the standard error. And so that can be quite a huge difference. That could actually widen your confidence interval a good amount, depending on how large the standard error really turned out to be. But the important thing is, now when we write this interval and we say the statement with 90% confidence, we are actually accurate. Without actually using T star, when we said 90% confidence, that was pretty much an approximation. It could have been more or less confidence depending on the problem. Well, any questions, folks, on getting that critical number? Okay, now let's check out what happens at 95% confidence. Again, just another preview. At 95% confidence, it's 1.96, and it really rounds to 4 decimal places. The sample size here is large, though, so we should be expecting a T star pretty close to 1.96. But there is always that extra error because of that. So we'll have a larger critical number for sure. Let's take a look. T star gets, then back to RStudio. We need to make a couple adjustments. We have different confidence and a different sample size. So to start, sample size is now at 120. Confidence is at 95%. And now it's all set up. Hit Control A, Control Enter, and it is off. Even at a very large sample size, we don't get 1.96, we get 1.9801. And again, that could be substantial, in fact. The more important thing is, we'll be accurate when we say 95% confidence now. We're not really saying 95% confidence when the confidence might have been 94%, for example. So it's at 1.9801. Well, that's how we get critical numbers. How do folks feel about that so far? Does it make sense? Awesome. There's lots of ways to get critical numbers T stars. On exam 3, they'll always be provided since it is a RStudio kind of problem. Doing it in the homework, you can do it from scratch or use this syntax if you like. Let's copy it in just in case. And now at this stage, we're pretty much ready to go to walk through an entire confidence interval procedure using this new method. Any questions at all, folks, before we take a look? Okay, my next example, word of warning, I think is kind of a silly problem. Think of this one as just a good one to practice on. It's about cloud seeding. Let me go to a new page on this one. Let's hide the method for the moment until we need it. So this one about cloud seeding says, to start, cloud seeding has been studied for many decades as weather modification. They tell us next, the rainfall in acre feet from 20 clouds that were selected at random were seeded with silver nitrate is given below. They said the rainfall, so these are all rainfall values in acre feet. This is the part of the problem that to me sounds kind of interesting because I have no clue how you select clouds at random. They just assured us that they really did it. This would take a whole gaggle of experts, meteorologists, and that kind of thing to say this really was a random or at least representative sample. So these are very hard things for us to study as outsiders looking into a study. If you see that kind of statement, usually we could just take it for granted and trust it. So I'll do that as well. It appears we have a random sample. I have no clue how they did it, but they are assuring us that the experts were involved and they have it. So here's the data from those randomly selected clouds, rainfall in acre feet. And they ask us the question, does the data provide evidence that the mean rainfall from seeded clouds exceeds 25 acre feet? Now, we could formulate this as a hypothesis test and answer the question. But for this one, we want to do it with a confidence interval using a complete analysis, which is an absolutely valid way to answer that kind of question. Think of this one as really a two-part question. We want to estimate the amount of rainfall from seeding with silver nitrate. We also at the same time want to see if our estimate includes exceeding 25 acre feet. It's more about the confidence interval on this one. Well, after we've done all that, let's state the practical conclusion, or excuse me, practical question. You can cite the question and just directly copy it in, put it in your own words. And it's usually something that's kind of a terse, fast kind of question. You might say, does seeding clouds with what they say, silver nitrate, no clue about the chemistry behind that, silver nitrate, increase rainfall? And I think that's a fine statement just as it sits. I'm not too picky on these, but if you did want to get picky with it, it's missing something. We're doing a hypothesis test estimating a population mean, a population average. So I probably want to say, does seeding clouds with silver nitrate increase rainfall on average? Just to convey, that's the method we're going to use. We're going to try to estimate the population's average rainfall. So that's a practical question. Next thing we'll do, and pretty much this is the same procedure so far that we saw in chapter 14 for a confidence interval. We need to say in words, what is the unknown parameter? We also have to pull in the context. This will help us when we write down the conclusion. But we're also going to do another thing on this one. It'll be up to us this time what the level of confidence should be. Sometimes a problem will specify a certain level of confidence. Other times, really up to you. So think of this as a choose your own adventure kind of a problem. Let's start with mu. We can always say, because we're dealing with numeric quantitative data right here, this is going to be a parameter mu, and it's going to be, you could say the population's mean, the true mean, or anything along those lines. I'll go with true mean. Mu equals the true mean, but we can't stop here because we have to say the mean of what specifically. Anyone see what should go next right here? The mean or average of what quantity? There's definitely kind of a trick to this. So if you're not sure, the way you can kind of track this is work backwards. You want to look at the data itself. But we have to be careful because we're not looking at the sample mean X bar of that data. That'd be a numerical value we actually have. We're just trying to describe the actual unknown parameter, this one down below. But when you look at that data, we can keep on working backwards and see the nature of that data. It was rainfall in acre feet. So we can come from here, look at the data, see the description of the data, and now connect the thought right here. It's the population mean. This is hard to delete for some reason. Let me try again. Population mean, amount of rainfall, you could put in the unit if you like, in acre feet. I'm going to try to write this statement kind of more terse, so I'll drop the unit for the moment. But even to this stage, it's not a complete statement. There's still something missing. Any volunteers for the last portion that we have to fill in? Absolutely, we want to state the confidence level. Let's go with C equals 95%. And in the chat, Jackson mentions all clouds seeded with nitrate as well. Yeah, exactly. So that's the thing that's missing right here. The purpose of that last portion that you mentioned was we're not interested necessarily in the rainfall in this area. We want to see what happens to the rainfall after we cause a change. And that means this is the thing we're interested in. What happens to the rainfall after we've changed the system by adding silver nitrate into it? So that's, in a certain sense, the heart of the study. And you might have noticed that that's kind of the purpose of the state phase as well. you mention silver nitrate down here, then it's another hint that we need to convey that somewhere in the parameter. It's the heart of the question. So good call, folks. We've got our confidence value, and now for our complete statement for the parameter, it'll go like this. Mu is the true mean amount of rainfall for clouds. It's clouds in a particular area, but they didn't mention as much. I'll again try to keep it simple by saying for clouds, seeded with silver nitrate. This is always a very tough thing to nail down exactly, but you'll find that once we get more and more into the course, it does get easier with time. We start to get a good feel for what to look for. But as always, I'll always extend the offer. If you're doing a homework problem and you're just not sure, send me an email right away. I'm always very happy to talk about the parameter to say if it looks right or if something is missing. Because if we don't get this parameter down really correctly, it will affect our conclusion for sure. But we've got down the major things we want to get through. Now we're going to turn to robustness. In chapter 14, the conditions weren't as major. In fact, chapter 14 had certain assumptions that essentially just said conditions will work out each time. We were only looking at them as a preview. But as a note here, in chapter 17, we will check conditions when possible. That already begets a question, right? When is it not really possible to check conditions? That's if you don't actually have the random data. So if that data is missing, there's no way for me to check robustness at all in this problem. All I can look at is to tell if we have a random sample or not. So now we're going to check conditions in earnest and look at those robustness conditions above. Let's take a look. Here they are finally, and I have a lot to say here because when you go to check conditions on any hypothesis test, there are certain things you don't necessarily have to say each and every single time. For example, this is something you should look for and mention if you can't find any information on it being random or not that will affect our conclusion. So we'll say here, for this portion, briefly discuss. In other words, you really don't have to say too much. You could just say the sample was random, the sample was a simple random sample, or no information was given about the randomness of the data. If that was the case, we'll just re-say at the conclusion that our conclusion could be challenged because we're not certain if the data was even random. For the next one, both mu and sigma being unknown parameters, this is not something you have to mention each and every time. Really, if you're doing statistical inference, that's the assumption that those are both unknown. And if you're using the procedure in chapter 17, sigma right there is specifically unknown. So here, you're not required to mention. Let's just say not required to discuss. So that's not looking so bad, right? On part one of the conditions, we're just going to say what we know about randomization. This is an implicit assumption, so you don't have to say the parameters are known. Now, robustness is the big part of this new test. We mentioned that we were trying to fix certain problems with our method. One problem was we were using a value of sigma, so we corrected it by putting in the sample standard deviation. But the second problem was chapter 14 assumed your population is distributed normally. That's practically a lie in almost every single real-world situations. But robustness allows us to now use the central limit theorem and state conditions where normality is not even a worry or a question about the problem. We're just looking to see if we match the robustness conditions. So let's make a big note here. For this portion, we'll carefully discuss and support with graphics. Think histograms. That's kind of a big purpose of what we were doing in chapters 1, chapters 2. Looking at the data, trying to decide how skewed it is, how symmetric it might be. It says here, If you have a small sample size, less than 50 as our author's benchmark, the t-procedures can be used if your data appear close to normal. Now, what we mean by that is we're looking for skew and outliers at the same time. If there is clearly a skew to it, if we can't say it's at least roughly symmetric, that is off the table, and our sample size is less than 50, we cannot use this procedure. It's not going to be effective. The problem is the shape right here is not going to be the t-distribution shape at all. It'll have skew itself. Here it's saying sample size at least 15 rather. So think bigger than 15 or equal to it, but less than 40 for the next bullet right here. So if you have a decently large sample size, you're going to be fine in almost all situations, except if there are outliers or you notice strong skewness. I think that's worthy of highlighting right here. We're not looking for any kind of skewness. A little bit of skew is normal in random data. It's to be expected. We're looking for skewness severe enough that we would never say at least roughly symmetric. We would say highly skewed at that point. If that's the case, and your sample size is at least 15 but below 40, we cannot use the t-distribution. It's not robust enough against that level of skew. But the central limit theorem does start to help. Right around sample sizes of 30, our author says greater than 40, t-distributions can be used even when the distribution is clearly skewed. But there is a limit to that statement. The amount of skew can become more and more and more. So if we have really large outliers, or seems to be a statement missing here, a huge amount of skew, then your sample sizes are not going to be robust enough unless you have huge sample sizes. Think 200 samples or more for huge amount of skew. But that's our conditions, and we're about to take a look at those in our problem down below. The downside to all that is, looks like we're kind of ran out of time. So when we come back, we'll see how to track these conditions really carefully. Right down here. It'll be kind of a review of what we did in chapter 1, chapter 2. So that's kind of relaxing work whenever you're reviewing something, and show how to check conditions very thoroughly. Well, any questions at all, folks, with where we're at so far? Okay, looks like a pretty decent stopping point for us. So just a reminder, when we return on Monday's class, definitely come armed with questions you'd like to ask or problems out of the review material that you'd like to point at, and it'll be another student-directed kind of review. If we run out of time, we'll just come back to here, but it's not meant to be a threat. If you have lots of questions, we can spend the whole time on Monday going over them. Well, have a great weekend, folks. If you have questions over the weekend, don't hesitate to write. I'll be a little bit more available since I understand we have an exam coming next weekend or next week. Thanks, folks.